Hello everyone, today we're going to talk about phase diagrams. A reminder, there are three primary states of matter, solid, liquid, and gas. In the solid state, the particles are closely packed together. In the liquid state, they are close, but there is still enough room that particles can flow and move past each other. In the gas state, particles are very far away from each other and are very free to move. Another reminder, there are 6 phase changes that you should be familiar with. Melting, freezing, vaporization, condensation, sublimation, and deposition. These phase changes go between each of the 3. There are 2 important properties that impact what state of matter a substance will be in. These 2 factors are temperature and pressure. Temperature is the measure of average kinetic energy that a sample has. The faster on average that particles move, the higher the temperature is. Pressure is a measure of a force that is applied over an area. In the case of dealing with particles, the force in question is the one that occurs when particles collide. So things where there are many collisions between particles have very high pressures, whereas things with fewer collisions between particles have lower pressures. So if we consider the gas phase, what would be ideal conditions for pressure and temperature for gases? Since gas particles are very far away from each other, they won't collide as often as they would in the other states, and so lower pressures are more ideal for gases. However, they are moving very, very fast, which implies that on average they have a higher average speed and a higher average kinetic energy. This means that gases should have high temperatures. So ideally, a gas would occur at low pressure and high temperature. Let us consider the same for solids. In the solid state, the particles are packed so closely together that they are almost constantly colliding with their neighbors. This means that solids have very high pressure. Conversely, they aren't moving as fast as they are in the other states, and so their average speed and average kinetic energy are much lower. This means solids have lower temperatures. So for a solid, ideally you want a higher pressure and a lower temperature in order to be in the solid state. What is considered high or low pressure or high or low temperature for a substance is unique to it, and that information can be analyzed from a phase diagram. The one shown here below is a phase diagram for carbon dioxide. The phase diagram helps you determine which state of matter a substance will be in under a given temperature and pressure condition. We will now explore what is on the phase diagram. Since this is a graph, the first things you should look at are the x and y axis. The x-axis is temperature. This could be plotted in either degrees Celsius or Kelvin, or on very rare occasion, degrees Fahrenheit. This one, shown here, has it in Kelvin, although you could also have one that is in degrees Celsius and it would still have temperature on the x-axis. The y-axis is then pressure, the other component to determining what state you are in. The pressure can be plotted using any of its possible units. The one shown here on the right uses bars, which is more commonly used when dealing with weather conditions. Other possible units include atmospheres, which is abbreviated ATM, pascals, abbreviated PA, which is the SI unit, kilopascals, millimeters of mercury, an older, more traditional unit, torr, pounds per square inch, etc. So those are the x and y axes. So your coordinates will be a temperature and pressure condition. Let us consider the shape of this curve. What shape do you see when you look at this curve? Many answers are usually given for what kind of shape this is. The 2 most commonly cited shapes are that it is a wishbone, like birds have, or that it is like the letter Y. In this particular one, due to the scale for the pressure, this one looks a little bit more like wishbone, but it would still also could look like the letter Y. I've also heard it described as a weird sideways H, although the wishbone and Y are much more common. You'll notice that the lines of this graph break it up into regions. There are 3 primary regions, each corresponding to the 3 states of matter. So we need to consider for the 3 primary regions, which one is located where. Since solids require a lower temperature and a higher pressure, we're going to want to look for a region that is closer to the left on the x-axis, but is further up on the y-axis. So that far left region is where the solids region is located. Gases require a higher temperature and a lower pressure, so we want something that is low on the y-axis but far to the right on the x-axis. So that bottom right region becomes gas. This means that liquids is in between. The lines then represent where phase changes will occur. You'll notice there are kind of three lines here that all meet at a point that we'll talk about in a little bit. The sublimation deposition line is the line that goes between the solid and gas regions. It is near the bottom left on the graph shown on this page. The melting and freezing line is the line that is between the solid and liquid regions. It curves from that point that the three intersect at up through the upper left and then curves off towards the right towards the end. The condensation vaporization line is then the line between the liquid and the gas regions. Again, it starts at that point where the three lines intersect in the bottom left and then makes its way to a point where the line stops. We are going to talk about why that line stops shortly. There are two key points that are on this graph, the triple point and the critical point. The triple point is the point at which all three states of matter are present and all 6 phase changes are occurring. This is the point where the three lines intersect that we mentioned before. If you'd like to see what a triple point looks like, there is a link provided on this slide that you can follow to watch a demonstration of what water looks like when it is at its triple point. The critical point is the point that is at the end of the vaporization condensation line. We mentioned that that line ends at a point, and then you'll notice there's kind of a dotted off region. At that point, it is no longer possible to determine whether or not the substance is a gas or a liquid. So we simply refer to it as a supercritical fluid, and that point at which we can no longer distinguish to be the critical point. The reason that we cannot distinguish is the pressure is now so great that it cannot be a gas, but the temperature is so high that it cannot be a liquid. Yet it still retains fluid properties, which are found for both liquid and gas states. They are both fluid states. And so it is some sort of fluid in that region that doesn't quite fit either of the two categories. So now that you know what the pieces of the graph are, you need to be able to analyze and obtain information from the graph. So our first example here is find the normal sublimation point for this substance. Firstly, we need to analyze what the word normal means in this situation. Normal means standard pressure conditions, which would be 1 bar, 1 atmosphere, 760 millimeters of mercury, 16 pounds per square inch, etc. Any of the standard conditions, which you will learn a little bit more of later. So on this graph, we're going to be looking for 1 bar. So we look and we find 1 bar. Because of how the axis is set up, 1 bar is where the x-axis is, which means we are going to have to do a little bit of guessing about where the sublimation deposition line would continue to in order to analyze this one. So carefully find the point where you believe the sublimation and deposition line would continue on a little bit to that bottom left until it reaches 1 bar, the x-axis. Estimate the temperature for that point that you just found. You'll notice on this axis that the marks go up by 50s, and so an appropriate estimate would be to do something that is something with a tens place, but not with a ones place. So an answer of approximately 180 or 170 or 190 Kelvin would likely be a very good estimate for where that normal sublimation point is. Let's look at a second example. At a pressure of 10 bars, what phase changes are possible for the carbon dioxide? For this, we want to find where 10 bars is on the y-axis, where pressure is, and follow an imaginary line straight across to see what lines do we run across as we make our way across the diagram at 10 bars. You'll notice we hit 2 different lines if we continue across in that way. The first line that we hit is the line between the solid and liquid regions, which means it is capable of melting or freezing. Then if we continue on past that through the liquid region, not long after, we would run into the line between the liquid and gas regions, which is for vaporization or condensation. We could also approximately estimate the temperatures of about 220-ish for the melting or freezing line and around 240-ish for the vaporization or condensation line. So this is how you interpret phase diagrams. Good luck.